Hi, everybody. So I was getting a lot of questions that were the same from some of you guys about Project Two. So I thought I'd like give you guys some background about, a few more hints, maybe some notes about what what the project's trying to do. So what the project's really trying to do is take you through the process of how you would use the logical effort activities that we talked about in the class, and how does that compare to simulations? So if you remember when we talked about the logical effort, and I'm going to talk about a NAND gate, but sort of chapter 4 of the book, and I think it's slide deck, I don't know, something like 9 that we had. So we said if you had a NAND in any process, in any CMOS process, you could compare it to an inverter in the same process so this delay of this NAND gate would be 4/3 H plus P for the NAND. Oh, sorry, plus 2. Okay, and this G refers to this effort, that the fact that a NAND gate is more complex, and it has these two NMOSes in series compared to an inverter. This refers to how much more difficult it is for the NAND to drive its output. So it would have a higher delay, given everything else being equal compared to an inverter for a NAND than an inverter. H refers to what the fan out of this is. So, for example, if you're driving, another 4 NANDs like yourself, or other things, refer to the capacitance looking in. So this is the fan out, and this was the parasitic. So the capacitance at this output node compared again to the capacitance of an inverter. So if you remember, and both of these guys, the core of the idea is that you would have a very simple model for a transistor. So an NMOS would be like a resistor with a switch and a drain capacitor. So R equivalent, C equivalent, ground, and then a PMOS would be something similar. It would have R equivalent P, this is R equivalent N, and it would have a C equivalent P, C equivalent N, and that'd be some gate capacitance here for both. So there's C gate and C gate. Okay, so we said, and so basically the idea is that you would represent the transistor as a simple resistor and a simple capacitor at its drain and a simple capacitor at its gate, or a linear capacitor. And so this 2 came from the fact that because you have more devices hanging on this node, this ended up being, what was it? I think it's 6 RC compared to the 3 RC here. So everything is referring, if you wanted, so basically you would end up getting this D for this delay for the NAND. And to compare it to a delay for the inverter, it would be just H plus 1 for the inverter, because in the inverter's G is 1. Everything is being referred back to the inverter itself. Okay, so if we were about to plot the NAND gate, the delay, the relative delay. And this is relative to an inverter, both of which they don't have any process information at a point. If you plot it as, function of h to 3, you can go ahead and plot it at h equal to 0. It would have a delay of 2. This is for just a NAND gate. So NAND delay. Okay, so it'd have 2. I'm sorry. At 0, it'd have 2. At 1, it would have 10 thirds. So it would be 10 thirds is like 3 and something. So it would be somewhere out here. And at 2, it would be 8 thirds plus 6 thirds. 2, 8 thirds, 6 thirds. That would be 14 thirds. So it'd be 4 something. It'd be like out here. So you'd have sort of a delay graph like that. But this is a relative number. So if you want to get the actual delay, you multiply this, whatever you have, whether it's, 2 or whatever that you come up with, whatever d it is, that's a function of h. You multiply this by 3 RC. Okay, the reason for the 3 RC is because everything is getting referred back to the inverter, and the inverter's delay was 3 RC. Okay, so that's the reason for the 3 for the RC. And the RC, we would have to find out for each individual process. It'll be different from process to process. Okay, so for example, and that's what we're trying to find out in parts 1 through 3 of our project. We're trying to figure out what the equivalent R's and C's are for our 0.18 micron process. Okay, and those are, again, this R is either R equivalent N or R equivalent P for, does it go up to here? So it's going to be as a unit per width of device, because if you remember, as we made these devices wider, if we made this N wider, so the width would be 10 times the nominal width, the R equivalent would end up being R equivalent divided by 10. So basically we want these values as per unit width. Okay, so the first thing we're doing here in problem, which one is it? Problem 1, I guess. Where is it? Here we go. So what we're doing is we're trying to find the equivalent gate capacitance for N and P type transistors. And because the gates get created at the same time in the process, the gate capacitance of the N is equal to the gate capacitance of P. Okay, so everything in this simulation that's suggested by your book as a setup, you have to still refer to the 0.18 micron process. So don't try to copy word for word what's in the book about the SPICE stack. You should be still creating the schematic and referring it to the 0.18 micron process that we used for project 1. Okay, so this is the reason the simulation set up. Okay, so you have, basically, you need to create a realistic rise and fall time, okay, for your simulation. And that's the job of this part. So this is, all this is doing is creating a a realistic input to your devices under test, which are these guys. These two, this guy and this guy, are the things you're testing. And the only thing this guy's doing is providing a realistic output for your device under test. Okay, so basically what we're doing is we are just interested in these guys here. And so notice a couple of things. One of them, first of all, it's easy to get confused here. These X's doesn't mean they're bigger than. This is just a name. The sizes, the relative sizes are these. So let's say this was a minimum size NMOS. This would be 4 times that size. This would be 8 times the minimum, 32 times the minimum, etc. So this device, so a minimum, whoops, let me write that down. So the width of N, the minimum is 300 nanometers. So a 32 is 32 times 300 nanometers, and I think that's something like, let's say approximately 10 micrometer width for the N type. And approximately, that means 20 micron for the P type. That's the width of this particular N32, and this is width of P64, sorry. Width of P64. Okay, so this is what this inverter is driving that load. Okay, so if I look at it, I have 10 plus 20, so 30 microns times the gate capacitance, which is in units of, farads per micron. Okay, that's this load that this inverter is driving. So driver X3 is driving this load. Okay, so 30 micron times this. So this is what we're trying to find, okay, in the simulation. And then notice that driver X6, so X6 is the same as X3. Look at the sizes here. It's 8 times N, 8 times N, 16 times P, 16 times P. So they're basically the same driver. They're being driven by the same input. They're being both driven by, at this node, C is the input to both. Okay, so if you start playing with the value of C delay up or down and look at if I plot as a function of time, so if I plot as a function of time, where should I put it? Here we go. So let's say as a function of time, I plot the node D. It's going to do something like this. Oh, something like that. And let's say I plot node G. Okay. If I plot node G and G looks like that, okay, what that tells me is C delay, whatever value picked for C delay, is larger than this value, because this guy is driving D. So this is, red is G and black is D. Okay, so this tells you that C delay is larger. Something like a plot like this would say that C delay is larger than than this gate capacitance, the total gate capacitance. And now let's say let's call this G1. Let's say actually it was like G was look like this, G2. That would tell you whatever capacitance you picked for C delay is actually less than this capacitance looking into this device. So you start tweaking the value of C delay until you're satisfied that you have something that, it's not going to be 100% matched, but something that's as close as you're going to get it. Okay, between C delay and D, basically between G and D. And then what that tells you at that point, once you've achieved that point, is it tells you that C delay is equal to 30 micron times C sub G F over in micron. And this is what you're trying to figure out. So basically this gives you the gate capacitance that we need for our logical effort here. So this gives you this value and this value, which are the same. Okay. So for this process, the 0.18 micron process, you only need to do this one time ever, and you have this value of C sub gate. Coincidentally, by the way, your book, if you want to cheat a little bit and look at what your book is suggesting this might be, you should look at table 8.6 on page 314 of your book. No, oops, sorry. I'm telling you guys the wrong table. Where's that table? Give me a second. It is table 8.5 on page 312. There's a column for TSMC 180 nanometer process. And you'll see that it's got a value for C sub G of, so this is from the book, table 8.5. Says C sub G as 1.67 femtofarads per micron. Okay, so I would say if you get anything between 1.5 and like 3, I wouldn't try to go get any sort of higher resolution simulations than that, because you're just kind of like eyeballing these graphs falling on top of each other. Okay, anyway, so that gives you C sub G. And then now you need to do C sub D. So you need to find this value, and this value. Now the C sub Ds, the equivalent N and P drain capacitances are different for N and P type transistors. So this here, so this schematic in your project in the book shows how you would go about doing this for a NMOS drain. And it's really the same as for the gates. So now you have a few guys that are creating a reasonable input. That's all these guys are doing. Okay, and the real work is happening here. Okay, again, notice that X4 is equal to X3. It's exactly the same size. They're being driven by the same node. Okay, so and then what you're doing here is you've put in a NMOS transistor. I would suggest you make it the same size as the NMOS. I don't know, the NMOS here. So maybe like a 32 times minimum. You want it to be large enough so you're not really looking for fine transitions. So whatever value you pick. Anyway, so what you want it to be is you want it to be an off device. and you're doing the same thing. You're comparing D and E, and when the transient simulation, the rise time for E and D equal to each other, it tells you that C delay is equal to whatever width you picked. Let's say you picked the 32 times, so it's a 10 micron device, times C sub equivalent N in per micron. Okay, and then from there you can get this value. And you have to do the same thing for a PMOS. So you do this first for the NMOS, and then the second time you do it for a PMOS. For a PMOS, you got to make sure it's also off. So I would hook it up like this instead of grounding the gate and source, because you want to just make sure it's off, and you only want to look at this value. Okay. All right, so that gives you the C equivalent N and C equivalent P. Now, the next thing is we need to figure out R equivalent N and R equivalent P. And this is where the book is suggesting you basically, you simulate this schematic once for, if you do it for, and they go through the math of this, but if you do, notice this is in units of H. So H is equal to 3 means you have this device, this guy is driving 3 devices like itself, and H equal to 4, it means that you're driving 4 devices like itself. So you can either make those devices 4 times bigger or 3 times bigger, or just plug in more devices that you're driving. And if you look at, so each one of them will have a delay. So this is, let's say we plot that, okay? So let's say I call this node in and I call this node out. So if I simulate that, what you'll see is in will go up. And so we're just looking at the falling. So the output will fall like, I don't know, like this. Okay. And so you want to figure out the propagation delay. This would be propagation delay rising. And it's from the 50% point to 50% point of these graphs. So the 50% point is 0.9 volts. So this difference gives you TPDR for H is equal to 3. And then you do the same thing for H equals to 4. So then you'll get TPDR for H equals to 4. And if you subtract those two from each other, then you basically get, it's equivalent to this equation. This C is C equivalent P. And this C is C equivalent N. Not quite. I think this will be sort of the average. But yeah, let's say let's call it the average. So this C, sorry guys, but this C is C equivalent N plus C equivalent P over 2. Not even quite. Sorry guys, I keep trying to, so it's 1C equivalent N plus 2C equivalent P over 3. So this is the average, sort of the drain capacitance you'll see. But from this, you'll get R sub P, because you have this, you have the C that you calculated from part 2, then you can get R sub P. And then again, you have the falling transition, because that you can also see that over here. It'll be like this transition here. So from there, you can get R sub N, and that you have the C from part 3. Okay, so that way, what you'll have is, once you're done with part 3, you have you will have you'll have this value, you'll have this value, you have this value, you have this value, you have this value, and you have this value. So you can actually then draw this graph as a function of actual delay, because you can then multiply whatever these numbers are. You can multiply whatever these numbers are by a tau, which is 3RC. And you have the R, you have the C, so you can multiply these numbers by that and get an actual graph of delay versus H. Okay, and then so that's the calculation 5A. Okay, and then you want to compare that to an actual simulation, and the simulation is you do an actual simulation of a NAND gate. You step through H's. I suggested H equal to 1, 2, 3, and 4, and get the delay through this actual device, and you plot that. So if you plot those two on the same plot for different H's, you'll get one for the simulation from the NAND gate, which is this blue guy, and you get one for the hand calculation, which is this orange guy. Of course, I'm marking it up in orange, but you get the idea. And that's sort of where that's the sum total of what you need to do. And so it's trying to, the whole idea behind this project is that we're trying to see how closely our hand calculations for logical effort, how closely they match simulation. And for example, this is something I did, I think last semester, and the slopes were similar, but there were some discrepancies in the absolute values. And you have to think about what explanation you might have for that. What else do I want to say? And then just lastly, just some ideas about, don't overcomplicate your simulations right off the bat. I would definitely start by just setting up your simulation, simulate just simulate one single inverter. And if you see anything that's above or below 1.8 volts or ground or significantly below, you should be seeing these kind of waveforms. If you see waveforms that are above VDD or below ground, or waveforms that aren't doing full 0 to 1.8 volt swing, it means that you're either going too fast or you don't have your VDDs and ground hooked up. And just start simple, make sure you are seeing what you expect to see, and take it step by step. Anyway, I hope that's sort of a useful recording, and good luck with your project.